I work on a project called Gyroscope, and Gyroscope is an upcoming stablecoin. It's in development. The current state of the project is we have what we call a proto system, which is, let's say, a simplified version of the system for technical testing. So we're looking forward to our mainnet launch. And what I want to talk today about is a certain stability mechanism by which the system automatically reacts to market conditions. And this is joint work with, let me activate this little laser pointer. All right. So this is joint work with my co-founder, Arya Klagesmund. By the way, in the announcement, there was a little mistake. I'm not at the University of Zurich anymore. I did my PhD at the University of Zurich in financial network theory, and then I did a postdoc, and then I got into DeFi. So I'm now full-time in the private sector. Right, let me start with the most simple model of a stablecoin. So a stablecoin is any crypto asset that is designed to hold a price of, let's say, $1. You could generalize that, but for our purposes, let's say $1. And this mechanism, in the very general sense, should always be, or must always be designed such that new units of the stablecoin can be created against something that has a value of $1. And existing units of the stablecoin can be redeemed against some kind of asset. And this is just the fundamental mechanism that should stabilize your price. And we call the mechanism by which you, like traders do this, the primary market mechanism. And so the thing that they can mint and redeem against need to be some kind of other assets. And now from this bird's eye view, depending on how your stablecoin is designed, these could be very different things. So in a senior shares design, this could be endogenous assets that are, let's say, on the fly being created for the purpose of doing exactly this, something like an equity share. In something like a design like Basis, for example, this could be a bond, basically. And in a system like Gyroscope, that is reserve-backed, so Gyroscope is a fully reserve-backed stablecoin, this is going to be some portfolio. And here, what I want to focus on are on-chain systems. Gyroscope is also a completely on-chain, non-custodial, like true DeFi system. Of course, in a system like USDC, for example, which has some off-chain components, some of these assets would be off-chain. And now we can think about how this systems should function in different market conditions. Let's say a boring example is when the system is fully collateralized, in which case this mechanism is very simple. In some aspects, you look into your reserve, you get some collection of assets that is worth $1, and when someone comes and redeems $1, 1 unit of stablecoin, you give them back the asset basket. The more interesting condition to which you need to respond somehow, and that I want to think about today, is what happens if your system is maybe over collateralized, but some of these assets might be illiquid. So you may not know their value very well, or they cannot be liquidated very well. And then, of course, there's the classical crisis where your system becomes under collateralized, and then what should you do? Let me give one instance of this schematic that's relatively simple, which would be the peg stability mechanism of DAI. So today, I didn't update this number, it might be slightly different, but on the order of 60% of DAI is basically a wrapper around USDC today. And then we have like another 20% that are LP shares that include USDC. So here the reserve would basically look like this, and you can redeem 1 DAI against 1 USDC. And so one motivation for Gyroscope was that we thought this type of design is somewhat suboptimal when you think about USDC is very stable empirically, but of course you should think about something like counterparty risk and censorship risk, which you inevitably have when such a big portion of your supply is backed by only one crypto asset. And so kind of the goal here is to kind of take this peg stability mechanism to the next level. The first thing that we're doing is we should diversify the reserves so that we have more than one or maybe two assets. And the second one is to have some programmatic risk control. So the PSM strategies, namely what you do when the system becomes under reserved, should be coordinated. There should be a strategy that's, let's say, global for all of them. And they should also be defined in advance. And this is what we call contingency pricing. This is going to be the main part I'm going to talk about today. How does the minting and redemption change when the system becomes under reserved? Maybe to add to that, the motivation for this is, of course, not that we expect this to happen a lot, but because we believe that there needs to be a contingency plan for the situation. And kind of the motivation is also this basic motivation in DeFi. Everything should be transparent and known upfront. People should know how the system responds. And that this is going to create trust in the system. So if you want to do this, there are a bunch of questions you need to answer, and as I said today, I'm only going to focus on one of them. Of course, the first question is you want this basket of assets. What should these assets be? Which risks are these assets exposed to? What structure should the reserve have? How do you manage risk in the reserve, and how do you generate yield? Of course, these things are somewhat related. And then how do you price the reserve assets? Because if you don't know how much the reserve assets are worth, you can't really do whatever you want to do. And these are all things we are answering in Gyroscope, and that the design has answers for that we hope are good. What I want to focus on today is something that excludes all of these problems. Namely, once you have answered all of these questions, how should your primary market mechanism work? And the main analysis tool to do this is what we call the redemption curve. And so what I want to do now is I want to introduce this tool, and then I want to use it to study some existing stablecoin designs. And then as the next step, I want to show you how we designed our own redemption curve in Gyroscope. So the redemption curve is very simply the price the price for redeeming 1 unit of stablecoin as a function of the total redemptions that have been going on over time. So basically this type of graph. And the ideal line, of course, looks like this. But if your system is under reserved, you cannot do this, because if you cannot redeem all assets at $1 worth of assets, because that's exactly what under reserved means. So any system that is under reserved has to have some type of function that decreases at some point in some way. The naive stablecoin would do the following thing. You would just say the redemption price is always 1. And at some point when my system is under reserved, I run out of assets, and then my reserve is empty. So you have this discontinuous drop here. And I think there are good reasons to believe that this is very unfortunate. Essentially, you're asking for a bank run because all of the holders of the stable coins know exactly that this is going to happen. And therefore, it's very advantageous to be the first one redeeming. And basically, after this bank run, this is the other problem. Your system cannot recover because your reserve has been emptied. Of course, things like this have happened historically and have been studied in finance literature, right? Where you had attacks on pegs of actual currencies, and at some point the central bank wasn't willing anymore to use as many reserves, and then you had this very strong price drop. Let me skip this slide. Now I want to look at some stablecoin designs that have been done in DeFi. And the first case study I want to look at is the original design of the Fei stablecoin. So Fei had assets stored in AMM, but they also had an additional mechanism called direct incentives, which would basically give you a worse redemption price at a time where many people were trying to redeem their assets. And actually what this does is that this makes the redemption curve very steep, which also means that the peg is not maintained anymore after the small amount of redemptions, right? So the quicker you decrease your redemption price, the more you protect your reserve in the case of an under-collateralization, but the less you also support your own peg, because if people can only redeem at 20 cents, then this does not improve the price of the stablecoin in any way. And this led to a very volatile market situation and basically a depegging right after launch. There's probably this thing I should talk about, which is Desiderata shares, in the spirit of Terra and Luna. And essentially, what you get when you do Desiderata shares. So Desiderata shares means that when someone comes to you with 1 unit of stablecoin, you have another token. So in the sense of Terra, this was Luna. You look at the market price of Luna and you newly create as many tokens as so many tokens so that the value of these tokens is $1 if you don't have price impact, and then you give that to the trader. Of course, doing this inflates your supply, and one way of looking at this is that there's a certain willingness of the market to absorb your endogenous asset, and at some point you will exhaust this, and then both the price of your Desiderata token and of your stablecoin is going to crash to zero very quickly. And of course, we have seen this very starkly in the case of UST. There's this one ironic timing. I gave the first version of this talk at FC at the DeFi workshop. I think on the Friday before UST crashed. So I guess in retrospect, this was all my fault. We have previously seen similar crashes, for example, in Iron and Titan, that was basically the same design. So now, kind of after these case studies, the basic idea we had for Gyroscope was let's start at the redemption curve, because all of the designs I've shown you were basically ad hoc designs. And sorry, I just got this message. And we thought, let's start at the redemption curve. Let's design our own redemption curve, and maybe then we can build something better. So the things I want to present to you is that we came up with a list of Desiderata that any kind of good redemption curve with good properties should satisfy. And then I'm going to show you one of these curves. And then we also want, from this curve, we want to derive an implementation in the actual system. And to do that, we need to do one more step, because if you look at some redemption curve, let me go back. Let's say this one. So a particularly terrible one, maybe this one. You see, we make this idealized assumption that you start at 0% redemptions, and you also assume a certain collateralization or under collateralization of the system, and then you look at what happens as people redeem more and more, but market conditions don't change. You only look at how the system behaves if market conditions, or let's say the value of your asset, stays the same. And so if we actually want to implement this, we don't really have this luxury, because there's suddenly timing, and we need to react to a situation where some people redeem and then maybe nothing happens, a few blocks pass, and then the next person comes and market conditions have already changed. And I'm going to show you how to do this. Kind of the mental model I want to keep here is the situation where the assets are an exogenous portfolio. So I want to exclude for now something like endogenous assets, Terra Luna style, that create endogeneities that make everything complicated and that we don't want anyways. So let me talk about Desiderata. basically what we need to think about is that there's this trade-off between supporting the peg for a long time in a time of under-collateralization and the eventual state of the system. If I say I want to support the peg even if there's a lot of redemption pressure, I run at a risk of exhausting my reserve. And then the viability of the system long term is going to be pretty bad. If I don't support my peg at all, well then I should think about why I'm even building a stablecoin. So the main ideas of these desiderata, I don't want to go through like the whole list, but the basic ideas is first, we want to protect the protocol. So what this means is that we want to make sure, or how we frame it is that the reserve ratio, which is the size of the reserve versus the amount of outstanding stablecoins, is above some kind of lower bound. And this is how we capture survivability. The basic idea is that maybe there's some collateralization ratio where we think if a protocol is collateralized at that percentage, then it has a chance of surviving long term. And of course, this depends on many factors, like what this number is. I think one thing is, say, fundamental economic value that the stablecoin provides. And this is also going to change over time, of course. The second thing, very closely related, is that people should still be able to redeem their coins at some amount. So the value of the coin should not go to zero. Of course, normally you want redemption at about $1. And then there's a somewhat technical condition that we think nevertheless is important. You don't want to drop the redemption price too quickly. Whatever you do should be kind of continuous and not too steep. And the main motivation is because then people might be able to speculate on it, similar to that Soros attack that I showed earlier of the pound in the 90s. And finally, we need to. So we have some other properties that we show about this. But the important bit is, of course, that we need to implement this on chain, and people actually have to be able to use it. So there are certain things that we just cannot do, and certain things we have to be somewhat clever about. Exactly. So in the paper we have the complete list. So now I want to show you the redemption curve we designed, and the first version is going to be a simplified version that satisfies all of the desiderata except for this one. And it looks like this. So we are given, oh great, PowerPoint, amazing. So we're given two parameters. The first one is the lower bound on the collateralization ratio. And the system will try to satisfy this if at all possible. Of course, if let's say this number is 80% and there was a big shock and your collateralization is at 50%, you obviously cannot satisfy this. But otherwise, the system is going to satisfy this. And then the system is going to do the following thing. At redemptions, so if there are 0 redemptions, the redemption price we offer is $1. And then we keep offering a redemption price of $1 up until some point. And then we're going to drop it to a sustainable level. And what this means is that we offer redemption at the collateralization ratio at this point. So for example, if the system is 60% collateralized, we would offer redemption at 60 cents at this point. And then we can do this indefinitely for as long as people want to redeem. So how does this work mathematically? We assume that there's, at the beginning, this collateralization ratio, and we call this RA. We will later call this an anchor point. And then the system does what I said. And what the system does is it chooses this parameter XU based on the function of RA. And here it makes this type of trade-off. The bigger XU is, the longer you can retain this price of $1, but the lower your final collateralization will be. So the system chooses XU such that this final collateralization ratio is exactly this lower bound that you're imposing. And then I think so in this case, this is the formula by which you do this, and you see it satisfies all of the desiderata. You get some lower bounded redemption price, you get some lower bounded collateralization ratio, and this is also easy to calculate. You can also set an upper bound on XU. You don't have to do this. If you don't do this, the system will always reach this as the final collateralization ratio, but you can also set an upper bound, and then it may up at some higher level.
Sorry, I have a quick question.
Yes.
So can you give some intuition about this XU? So for example, if I'm decreasing this XU, I should expect your R to be increasing, right? Then wouldn't we be at a point that it won't be discrete anymore, but you will have a continuous redemption curve?
Let's see. So you keep this one fixed, the initial collateralization?
Yeah.
Okay, and you push down XU. Yeah, then this line is going to move up.
Mm-hmm.
And I think what happens is that, so if your system starts under collateralized here, if XU moves to 0,
right,
this is, well, where's this going to converge? Well, I think the height here is going to converge to your initial collateralization ratio.
right.
This is 80%.
But that will be lower than 1, right?
Yeah. Exactly.
Otherwise, okay. Got it.
Yeah. Maybe in the next version of the talk I put a line here for the RA. So the initial collateralization would be somewhere between 1 and this.
Right. Yeah.
And so as long as you offer $1 redemption, the collateralization of the system is going to decrease.
Cool. Thank you.
Right. So where was I? Yeah. So this satisfies all of the nice desiderata, but of course it has this nasty discreteness here. And so to fix that, we're going to introduce a linear segment. And then the whole thing looks like this. PowerPoint strikes again. Sorry for this messed up table. So basically, the idea is that we make this continuous by introducing this linearly decreasing segment here. And now, unfortunately, everything gets much more complicated because now we have two parameters that change this the shape of this curve. One is still this value XU that tells you for how long do I offer a redemption price of $1. But then you also need to find out how this slope should decrease, and we call the slope alpha. And so these are going to be two derived parameters that the system derives from this initial collateralization. And again, you can parameterize this. You still have these two parameters here. And then you can also impose a lower bound on the slope of this linear segment. You don't have to do this, but if you don't do this, then for high collateralization ratios that are, let's say, just a little bit below 1, the system is going to be somewhat degenerate, I think. Right, and then, so if you want to compute these two parameters as a function of the initial collateralization, you also need to kind of trade them off against each other. And the trade-off we defined was that first the system tries to make this linear segment as flat as possible, because we felt it's just very important to have a behavior that is not abrupt up to like until this lower bound here. And when this lower bound is reached, then you can start maximizing XU and stabilizing the peg like this. I guess there are other options to define the priority between the two parameters, but we chose this one. And then, so what you actually get here is 2 points. Before we only had one interesting point, now you have 2 points. The one is this XU, the point up until we support a price of $1. And then you basically walk down this linear segment up until a point XL, where the collateralization of the system is equal to the redemption price. And this one is always going to exist. And then you offer redemption at the collateralization ratio, so you don't go further from there. And now, once we've done this, the math we get is this, which is of course a complicated mess, but it's not, at least it's not very complicated to compute. You see that none of these expressions are very complicated. We have some case distinctions. So we have some case distinction here when one of the parameters reaches the bounds that are defined as hyperparameters. And then within the calculation of whatever is in these like maximum and minimum expressions, we also have another case distinction. And this is going to become important later. So this was what I've shown you so far, and I'm going back to this image because it's more visual. What I've shown you so far is how do you compute this idealized redemption curve where we are, again, given as an input the starting collateralization ratio, and then redemptions happen, let's say over time, without any market conditions changing. And so the next, let's say part of the presentation would be what do we do if market conditions do change? Would you, Kite, would you like to ask a question about this, just in case?
Yeah.
No.
Go ahead.
Yeah. Okay. Okay. Great. Exactly. And so to make this dynamic, the first thing you need to do is to replace this redemptions variable here, because of course what we could do is just sum up all the redemptions that have happened since the beginning of time in our system, but that would be a very strange measure, because something that happened 2 years ago would affect us as much as something that happened yesterday. So instead what we do is, what we really want is some kind of time-weighted redemption pressure. And so we replace this variable by a time-discounted sum. So there's some kind of discount factor. You look at all points in history, and you sum that with an exponential weighting. And so the measure we take from this is something like current time-weighted pressure on the reserve, which we think is very useful. And this also has a nice feature that it's very easy to track on chain. So you don't actually have to compute this sum, of course. And now I'm going to show you what the system does. And we need to change a little bit the world we're living in right now. And so what I assume is that what we can observe at any point in time on chain are two things. The first one is the current redemption pressure, and I call this X, and based on this time-weighted sum. And the other thing we can observe is the current collateralization ratio, and I call this R. And now what we're going to do is we're going to use the redemption curve design from the previous part as a model. And what we're going to ask is, what is the initial collateralization, this anchor rate, or RA, that would have brought us to the situation we're currently in? And of course, what's easy is the other direction. So if we are given RA and we are given X, then what we can do is we can look at the redemption curve from the previous part, we can integrate that, and then we get the collateralization ratio at each point in time. And we can also do the reverse. And there are kind of two parts to this. The first part is the mathematical part, and the other one is the computational part. And the mathematical part is pretty easy. You just prove that the collateralization ratio at some redemption amount is strictly monotonic in your initial redemption pressure. And that's not super trivial. So there's actually something to prove here. It's also not super complicated. But what you need to keep in mind is that if you change this initial collateralization, then your redemption curve, so this one, is going to morph because this parameter alpha and xu are going to change. And so basically what you need to show here is that even if these parameters change, the effect is still going to monotonically affect the collateralization ratio at some redemption pressure x. But once you've shown this, you immediately get uniqueness, which is great. Or I should say that you get uniqueness outside the bounds of a situation that's trivial. So if the current collateralization R is less or equal this parameter, which was the minimum collateralization you want from the system, then this is no longer true, but then you also don't need to do this whole complicated construction, because what the system would do is it would just see, oh, I'm already at my limit. I'm gonna collapse my redemption curve to a line. So this was kind of the, let's say, the math side of this. But now, how do we actually do this? And how do we do this with a finite number of operations? And to do this, we actually need some additional structural results. And what we did is we split this redemption curve. Sorry, was this a question?
Yeah, there's a question in the chat.
Oh, yeah.
Can you remind me what the blue and green line is showing?
You mean in this particular picture?
I think the previous page.
Oh yeah, I haven't explained this. Sorry. I'm going to explain it now. Now is actually the perfect time to ask this question.
Okay.
Thanks. Yeah, sorry, I put the wrong picture in there. Right. So what we can do is we can split up the space of x and RA values, and therefore kind of this whole surface, into different what we call regions. And the motivation for these regions is based on these case distinctions I mentioned earlier. So basically, let's say the very basic motivation is that if you integrate this redemption curve and you plug in these equations for these alpha and xu variables, and the only remaining free variable is so here it's like written down a little bit differently, but the only remaining free variable is RA. But the problem is that with all these case distinctions, these like whatever comes out of this is very complicated and very hard to handle mathematically. So basically what we say is we define regions, and within a region, all of these case distinctions fall into the same case. That's basically the definition of a region. And now, of course, you kind of need to take like the cross product of all these different things, and then you get a bunch of regions. And then you also have another case distinction here, because this is a piecewise linear function. So you have basically a case distinction where the x is between this point and this point, which is xu, or if it's in this linear segment between this xu and xl, or if it's in this final constant segment. So this would give you another, let's say, dimension along which you need to distinguish regions. So the result is going to be that you can detect in which region you are only knowing the current collateralization ratio, but without knowing this RA value. And then fine. So maybe let me go a little bit more into detail about how we do this. And there are kind of two sets of regions we need to think about. The first thing, so these like blue and green and black and colored lines are just the boundaries between the different regions. And these labels yes, we labeled them using a combination of 3 letters. I don't think I need to go into the definition of the letters, but they are just because they are basically the cross product of different case distinctions. And you see that some of these lines are parallel to the X dimension, so they actually don't depend on X, but they only depend on the RA. And these are all of the distinctions that only depend on the things on this page. So for example, what I could do is I could distinguish between this case and this case. And what I do is, well, there's a case where RA is greater or equal than something. There's a case where RA is less or equal than something. So the boundary is going to be where RA is equal to the thing. And then I have one specific RA value. And I can do the same thing for many other things. I can also do them here when you kind of resolve this, and for everything else on here. Sorry, I can jump back. And so for these parallel lines, what I can do is I can actually go and compute these values. I could pre-compute them and store them on chain and then just access them. It turns out that these calculations are not so expensive that you would actually do this, but I could. And then if I have a certain value X, then I want to, let's say I have a certain value X, and I want to distinguish if I'm on which side of this black line am I can just compute what would be the value that I would have on that line, and then I can decide if I'm below or above it with my R value. So that decides you on which side of the region you are for all of these things. And so the complicated thing that kind of remains are these lines, and they result when you take basically the piecewise linear nature of this line, and you accept the fact that the parameters of the piecewise curve depend on this RA value, which you have here. And then you ask in which piece am I, the first, second, or third piece. And then the boundaries between these regions are actually going to look like this. And so deciding, if you don't know RA, deciding on which side of these lines you are is actually a little bit more complicated and requires a bit more structural results. Essentially, it turns out that you can do some case distinctions and you can replace RA by R, which you know, and you still get the right result. I don't have good intuition for this, to be honest, why this is true. So once we know in which region we are, what we can essentially do is we can reconstruct the function that computes the current collateralization based on RA within that region. And then we see that this is actually a pretty simple equation we get out of that. And it's actually quadratic. And so once we have the region, we need, I think, one square root. I think the number of operations we need for this is basic arithmetic comparisons, and then I think we need one square root to find the region and another square root to compute the RA. So once we've done this, we have done all of this to reconstruct our anchor point, and from this we have reconstructed our redemption curve. And now when the user comes to us in the current block and they want to redeem a certain amount, what we can do is we essentially go to this curve. We know that we are at some starting point. Let's pick this one. And then we essentially see if they want to redeem a certain amount, by which amount does this increase the redemption pressure X. This is just an offset. We compute, we know the R value here. We compute the R value according to the redemption curve at the offset. And then from this difference, we can compute how much we should redeem. And in that way, we compute the actual redemption amount, which is what we need to do. Right. So this is essentially the algorithm. If you write it down, you get like 2 pages of equations, and we have implemented this on chain in Gyroscope. We are running this in our proto system, and so well, it's working well. We have a few other properties that are, we think, quite desirable. The first one is a path independence result that's mathematically very straightforward. And that's just because, so if we compute a redemption amount as an integral over a certain curve. And what this immediately implies is that if you redeem a certain amount and then you redeem another certain amount, then this is the same as redeeming the whole amount because integrals add up. But that's actually a very nice property because it means that it's an argument against manipulability of the system. People don't need to think about, do we want to bundle our redemptions or something like that. If you extend the model a little bit to a situation where people can mint and redeem and do that in some order and follow like paths through the mint and redeem space, you get a property called path efficiency, which is, let's say, an extension of this. And here you can prove that the protocol state measured in a certain way only improves over these paths. So that also means you can't really be strategic about this. But even if people are not strategic, this is just good for the protocol. Math looks like this. So with this, I want to conclude, and happy for any further questions. To remind you, I talked a lot about redemption curves in this talk, which is the price that the system offers in exchange for a unit of stablecoin as a function of the amount that has been redeemed. The basic idea is to design a redemption curve that has desirable properties, and I have shown you what our redemption curve design looks like, and how to make this dynamic and how to implement this. In Gyroscope, this whole thing is called the Dynamic Stability Mechanism, or DSM. If you want to look at the paper, that's here. And I have one thing to ask. If you want to get involved, and it would be really great if you would like to, Gyroscope currently has a community or an early DAO of about 3,000 people. We have launched this proto system that I talked about. And so if you want to join, if you want to learn more, if you want to try it out, you are very much invited. You can actually go and create some gyro dollars. It's a capped system, so everyone can mint up to $10 worth of gyro dollars. We did this to make clear that it's really kind of a technology test, and that you shouldn't go and put your life savings into this. And what's going to be upcoming in the following months is a wider, let's say, bootstrapping of a governance system. Gyroscope is going to be DAO controlled from the beginning, and then the launch maybe, let's say, in spring this year. So thank you very much for your attention.